Hi guys, welcome back to my channel. In this tutorial, I'll be taking you through applications of differentiation problems. This is a review exercise to prepare students for exams. The first question says, a water tank has a shape of an inverted circular cone with a base radius 2 meters and a height 4 meters. If the water is being pumped into the tank at a rate of 2 meter cube per minute, find the rate at which the water level is rising when the water is 3 meter deep. So these are real life applications of the differentiability we've learned in calculus. And to solve this problem, let's first graphically represent this problem. So an inverted circular cone will have its base like this, right? And it's pointed this way, right? So you're having an inverted circular cone with a base radius. So from the center here, so meaning that from the center to any side here is 2 meters, right? Then it went ahead to say that it has a height of 4 meters. So a height 4 meters and a radius 2 meters. So you just draw your height from here to the side, right? It's 4 meters. Then if the water is being pumped into the tank at a rate of 2 meter cube per minute, we can just illustrate some kind of a pump somewhere which is pouring the water in it. Okay, then find the rate at which the water level is rising when the water is 3 meter deep. So we can just locate our 3 meter level somewhere here. So probably our 3 meter level here, right? So from here to the ground is represented as what, 3 meters. And this here is the water level. Okay, this here is the water level. So let me say this is the water level, right? Yeah. So now, what is the problem? That's the first thing you should ask yourself. What is the problem? The problem starts at find. To find the rate at which the water level is rising. So what is rising? We are looking out for the height. So meaning we are looking out for the h on the t. So this is the whole problem you are looking out for, the h on the t, right? But in the problem, we're given 2 meter cube per minute, and that is signifying what? The change in volume per time. So you have been given the v over the t to be equal to 2 meter cube per minute. So let's see. Find the rate at which the water level is rising when the water is 3 meter deep. So we are looking out for the h over the t, and from the question you have been given the v over the t, right? So now, how do you relate these two parameters? After drawing, you put your available information down. How do you relate these two parameters? So using chain rule, you know that the v over the t is equal to the v over the h, right, times the h over the t. So when you have your chain rule, you know that to find a change in volume per time, the other parameter which keeps on changing is the height. Is that not it? The radius is not changing, right? I mean, our middle radius here is not changing. So we are not interested in the radius actually, because we are looking out for a changing level of what, the water. As the volume of water comes in, it only alters the height or the level of the water, right? But not really affecting the radius of the original container. Okay, but though at any level the radius will be different at any level, yes, but you're looking out for the effect at which the water is changing. So we have only two parameters. The water itself will change in volume, then it will also affect the water level, which is of interest as our height. So meaning that to find a change in volume over time, we have to equate it to the change in volume over the height times the change in height over what? The change in time. From the problem, we are looking out for the find the rate at which the water level is rising, meaning we are looking out for the h over the t, and that is the whole goal. So we have to put this one down to guide us, right? So you come back to this. Now, remember that when you want to find the v over the h, so you see from the problem, we are having some parameters here given. I have the v over the t given. Is that not it? My v over the t is given. And the h over the t is what I'm interested in. That is what I'm going to find. So meaning the next thing that I should tackle is what? The v over the h. That's the most important. So the v over the h. That is what I have to look out for. Now, what is the v over the h? For the v over the h, we have to what? Differentiate our what? Volume of the inverted cone with respect to height. What is volume of a cone? Volume of a cone is giving us one third the volume of what? A cylinder, pi r squared h. So meaning that to find the change in volume of this with respect to height, our parameter should be in what? In height. We can't ignore this. If we differentiate this with respect to h, r becomes a constant. But we really want to make this whole function here be in terms of what? V and h. Initially, as I told you, we want to only have the two changing parameters. So meaning that we have to make this r here the subject. We have to make this r here the subject, right? And represent it in terms of what? H. So that we can have a function of what? H. That is a function v of what? H. So that we can easily differentiate with respect to what? H. Now let's see something here. So at this point here, I need to make R the subject. How do I make R the subject? So let's use our proportion here. Now I have a bigger height, 4 meters. I have a bigger radius, 2 meters. Is that not it? So I'm making some relationship here. Capital R over capital H should be proportional to a smaller r over what? Smaller h. Okay, using similar triangles. Because at any time, at any instance, you'll be getting similar triangles. If you come here, you'll be getting. So they are all similar triangles. So using similar triangle approach, you realize that at any instance, the smaller r over the smaller h should be equal to the bigger r over the bigger h. Is that not it? From the problem, we were given a bigger h and a bigger what? R, right? Those are the parameters of what? The cone. And that is what we were given. So my r was given as 2, my h was given as what? 4, right? Should be equal to my smaller r over my smaller what? H, right? So from here, don't be tempted to say that the height of the smaller one is 3 meters. No. Now the thing is, we are looking out for something here. We are trying to draw a relationship between what? Our r and h. But don't forget that we want to find an expression of r in terms of h. That is why we are doing all this. So if you bring the value of h as 3 meters, then obviously we can't make, it's not going to really affect our change function. This is a function, so we actually want the parameters in the function. Okay, we are not moving straight to find the value. No, we want a function, how one variable is changing with respect to other. So at this point, I want to find how this my radius is changing with respect to what? H, or the relationship between the radius and the height. Okay, so don't be tempted to be using these 3 and 2. Okay, sorry, these 3. So at this point, we have to make what? R the subject. Is that not it? So my smaller r will simply be equal to this half, right? So h over 2, because already this will cancel and this will give me what? Half. So I'll simply have r is equal to h over 2. Once you have this down, you come and make the subject into your volume equation. So you know that your volume is equal to 1/3 times pi times what? Your r squared. And now I put my h over 2 here, all squared times my h. Is that not it? So my volume simply becomes 1/3 times pi times h squared over 4 times h. Is that not it? Yes. So at this point, I keep on with the simplification, right? I'll just multiply everything all here. When I multiply everything, I'll be having the 1 out of 3 multiplying what? The 4 here. So that I'll get my V to be equal to 1 over 12, right? 1 over 12 times pi. Then the H will be Q. Take note. The H will be Q. So this is it. As simple as that. Right. So the H should be cubed nicely as this. So this is my function, the volume function with respect to what H. So at this point, the only thing I have to do is to find my dV over the H, right? So my dV over the H simply becomes, when I differentiate this, remember I'll have 3 multiplying 1 over 12 by pi, then H squared. Is that not it? As simple as that. 3 will go into itself 1, go here 4. So therefore, my dV over the H will simply be equal to, now I'm having only pi on 4, right? So pi H squared all over 4. So pi H squared all over 4. Pi H squared all over 4. So once I have this expression here, meaning that I'm almost through. Is that not it? Meaning that I'm almost through. I'm almost through. So at this point, I'll come back to my chain rule here. Okay, I'll come back to my chain rule here. So let's see. So let's see what we're gonna do here nicely. So my chain rule, it says dv over dt is equal to dv over dh times dh over dt. Dv over dt was given in the problem as 2 meter cube per minute, right? 2 meter cube per minute. So let me write my 2 here. Should be equal to my dv over dh, which is what? Pi h squared over 4 times dh over dt. Is that not it? Yes. So at this point, I'm having we are looking out for the h over the dt. So we simply make that one the subject, right? So making the h over dt, I'm simply going to have my dh on dt to be equal to 2 over the expression pi h squared over 4. That's my first division. So at this point, what do I do next? I just have to simplify this expression. I just have to simplify this expression. So simplifying this expression, we know where our h is, right? We know where our h is, so we can easily make substitution for our h. So the h over the t will simply be equal to 2 over the expression pi times, this one is, our h is the height we're given in the problem. Remember, the height we're given in the problem, the height of the water. At this point, I told you that we could have used the height of the water, which was 3 meter deep. We could have used it, but because we want a function in terms of h, we assume that we don't know. That is why we gave r over small h, the small r over small h here, so that it will be in terms of h. Okay, but the actual height we're given is what the water is at 3 meter deep. So if you want the h over the t, we simply have to use the one we have. So pi, then my h squared is here, so I'll put my 3 squared, right, all over what? 4, all over 4. So I can keep on simplifying this, and this simply 2 over the expression. I have my pi times 3 squared is what? 9 over what? 4, right? 3 squared is 9 on 4. So we keep on simplifying this expression. So you just have to take your calculator, then you punch this expression in it. Punch this expression in it. So if you have the fraction 2 over, So 3.142 for pi times 9 on 4. That'll be giving us 0.2829, and since it's height, meter per second, right? So meters per second. Don't know why. 0.2829 meters per second, right? So that is our change in height with respect to what? Time. Change in height with respect to what? Time. You can also leave your answer in pi, or you can choose not to simplify this pi, but leave it in that form. It's all the same. It's all the same. So having answered the first problem, let's move to the second problem that we have. Move to the second problem. So let's see. So what is our second problem? So our second problem says a cylindrical can is to be made to hold 1000 centimeter cube of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay, so let's see. As I told you, before you start, you have to represent this in a diagram form. Okay, so that you can easily pictorially picture, right? Pictorially picture, yes. Okay, so a cylindrical can, right? You want to make a cylindrical can. This is a cylindrical can. It should be made to hold 1000 centimeter cube of oil. So the volume that it should contain be 1000 centimeter cube. Find the dimensions that will minimize the cost of the metal to manufacture the can. Find the dimensions that will minimize the cost of the metal to manufacture the can. Right. So this is a nice problem. Right. This is a nice problem. So we are looking out for just the parameters. So this is what we call optimization. Optimization. We are trying to optimize our what? Dimension, so that the cost of the metal will be minimal. And this is one important application of calculus in the industry. Whatever you want to bring out, you have to optimize it so that you can know the parameters when you use, you get the minimum cost, or that will yield the maximum cost, right? So this is a real life importance of calculus which you should be able to apply. And let's see. So for this one, we know that the volume here is what? 1000 centimeter cube, right? That is what you have been given. And you are looking for dimension. What are the dimensions we need? Remember that for a cylinder, what are the some of the dimensions? You need your radius and you need your what? Height. Is that not it? So for the surface area of a cylinder, surface area A, you are going to have something like, there is 2 circles. See, 2 circles. So you say that 2 pi r squared, because you are going to have 2 pi r squared, right? 2 pi r squared. That will be the area of the two here, the two surfaces here. Since it's going to contain let's say an oil, it maybe a closed cylinder. In the industry, you can have two closed cylinder like this, and there'll be some tube connecting which will be pumping oil in it, right? There's no way you're going to have only one side open or anything, no. So sometimes this alone should give you a clue on what is expected in the problem. Once you are dealing with a cylinder to hold an oil, just have in mind that it is going to contain everything here. It's going to contain everything here. So the parameters we need is the height h from here to the ground h, then also the radius r for each side, which is the same radius r. Is that not it? So the surface area is 2 pi r squared. That's the surface area of the two closing surfaces. Then the actual middle area like this, the surface area is given as 2 pi rh. Okay. So once you have this surface area formula, the next thing to do is from here, you move to the formula for the volume. Because to find the parameters R and H, we can get it from this, our volume and our area. Okay. So our volume here is given as, for the volume of a cylinder, it's given as pi r squared h. Okay. So in optimization, we have the objective function. Objective function. Then we have what we call the constraints. Constraints. Okay. So when you say objective function, this is the function you'll be handling for our calculation. That is what you substitute variables and parameters into it. But the constraint is what limits us. This is how far you can go. Right now, I'm going to create a cylinder that will contain a particular volume of what? Oil. That volume of oil will limit you the amount of material you can use, will limit you everything. So we call it a constraint. Okay, it's trying to give you the level with which you can go. Right now, the cylinder is going to contain thousands and cube of oil. You can't do anything that will waste volume. Okay, if you create it and it's now having a capacity of 2000, see, it's just a waste of volume, right? So meaning that our focus is this, volume this, and this is what we call the constraint. So our volume pi r squared h is simply equal to 1000 centimeter cube. Now, what is the next thing to do? Our objective function is the surface area. That is what will help us to get our parameters. So from the constraint, we know that volume is equal to 1000. Okay. So now I can make my height the subject. So my height to be equal to 1000 over what? Pi r squared. Is that not it? 1000 over pi r squared. Then I will substitute this into what? My objective function for it to be optimized. So my objective function, which is a, is equal to, I have 2 pi r squared here, 2 pi r squared here, plus 2 pi r, but the h here becomes what? 1000 over pi r squared. Is that not it? Yes. So at this point, what do? I need to simplify. Simplifying this, you realize that this pi will cancel this pi, r will cancel one of the what? R's, and I'll get one r here. This will go. So my objective function a simply becomes 2 pi r squared plus 2000 over r. As simple as that. Plus 2000 over r. As simple as that. So let me clean this side. So now that you have our objective function, let's see how we are going to do the optimization. Remember that in calculus, whenever you are doing minimum and maximum, you need to find what we call the critical point. So the minima or the maxima of any function is at a critical point. Remember, so at a critical point, you know that changing what the variable with respect to what another variable is zero. Is that not it? So we are going to differentiate our a with respect to r. At the point where this function is zero, we are going to get the critical point or the extremes of this function. Since we want the minimum cost, meaning we are looking at for what? The value of r that will make our area become what? Minimum. That is the application. Okay. So at this point, let's see. Our dA over the r. What happens to it? When I differentiate this with respect to r, what am I getting? I'm going to get something around 4 pi hot r. Is that not it? 4 pi r. Then this side, remember this is r to the power negative 1. So we are going to get minus 2000 over r squared. right? Then you know that at the critical point, this should be equal to 0. As simple as that. Once this is equal to 0, I'll have 4 pi r to be equal to 2000 over r squared. 2000 over r squared. So at this point, this r will cancel 1 and will cancel one of these r's. If you can. Then my actual r will simply be equal to this r. When I bring this r, I'll bring the 4 pi here. I'm going to have 4 pi. Sorry, there is something I have to correct here. During the differentiation of this is r to the power here I had there was a mistake here because at this point, right? At this point, once I differentiate, I had what? R squared, right? And this is what I'm going to do. Let me reverse this here. I can cancel that straight away. So this happens to be a quadratic equation. So you have to handle this well. Sometimes you are supposed to get two roots, right? Then you just do some cancellation and it will take away one. That is not how we solve that. So remember that whenever you get such situations, you multiply through by what? The coefficient. That is should be the most important. So you're going to get 4 pi r cubed minus 2000, right, is equal to 0, right? So this should tell you that you're looking at for three roots, okay? So you simply get 4 pi r cubed is equal to 2000. Then at this point, I need r. So r is simply be equal to the third root of the expression, 2000, 2000 over what? 4 pi, right? So this is giving me my r, 2000. So just find the square root of the third root of the expression, 2000 over 4 pi. And that's giving me 5.4, 5.419, right? So 5.419. So 5.2, 5.42, 5.42. And our parameters was given in centimeter cube. That's our volume. So we are going to leave this one into centimeters. So right now we have our radius given, right? We have our radius given. Okay. So once we have our radius given, we are simply going to find our height. Then we are done. Okay. So remember that this was the value. This is the critical point to be getting. But this is a repeated root. So actually, this will be the only one we have. So there is no need for us to simply be testing for two values. So once you have got this, we simply have what our radius at the critical point. So this is obviously the minimum what point. Okay. So now the next thing to do is to find the corresponding height that will give us what the minimum as well. The corresponding height that will give us the minimum. So let's see how we do that one. So at this point, since we have our r, you know that our h is equal to, from this one, right? Our h is equal to 1000 over pi r squared. Is that not it? So to solve this, we simply have the answer to be 1000 over my pi, as you know, is 3.142. Yes, 3.142, right? Times my radius squared. What's my radius? Now my radius is what? 5.42. Okay, 5.42. Then you simply punch this one into the calculator and you should expect something like 58.74. And since it's height, centimeters, okay, centimeters, right? So I think my system is trying to corrupt me too much. Kindly bear me out. So We now have our height and radius. So our radius is simply 5.42 centimeters. My M keeps on cleaning, yes. Then my 58.74 is also, yes, centimeters. So these are the two parameters you are looking out for. That's all. So the question was like, we should simply find what's the dimension. So the dimension is simply the radius as well as what the height. That is all. The radius as well as the height. So that is what you should take note of. So let's move to the next problem. The next problem. So let's do some cleaning here. Okay. Okay, so let's see. We are moving to question 3. Question 3 says that find the interval within which this function is increasing and decreasing. So let's write our function down. F of x is equal to the expression 3x to the power 4, right, minus 4x to the power 3, right, minus 12x squared, minus 12x squared, plus 5, plus 5. Let's see. So f of x, let me write it here. Okay, so let's continue with the third one. As I said, find the interval within which our function here is increasing and decreasing. Okay, so how do we do this? Function f of x is equal to 3x4 minus 4x to the power 3 minus 12x squared, then plus 5. We have to find whether this function is increasing or decreasing. And remember that if you say a function is increasing or decreasing, it all depends on the radius. Sorry, the gradient function. Gradient function. Gradient function. Okay. So you just have to differentiate this function. So it all depends on the gradient function. Okay. So once you have the gradient function, you know that a function on, let's say, let me draw something like this. Yeah. If you have a function like this, okay, it means that one parameter is here, let's say h, another parameter is here, let's say t, okay, let's say t. You realize that the change in h with respect to time give us this whole graph. But at this point, h was changing, was increasing, right? As time was also increasing, was increasing. Then now h came down back again, like that. So meaning that if you want to see the increasing portion, once we get the derivative, or once we get a change in h over t, it should give us something what greater than 0, okay? Something greater than what 0. And once we get um the h over the t giving us something less than 0, it means that it's decreasing. That is the whole idea. So once your derivative is greater than 0, it means it's increasing, and once your derivative is less than 0, it means it's decreasing, right? So how do you do this? The very first thing you have to do is to find your critical point. Your critical point. So finding your critical point will guide you to know the peaks know the peaks, then you based on the critical point to solve the problem. Okay, to solve the problem. So now what are the critical points? We simply have to differentiate our function. So what is the fx, right? Fx over what? X will give us, the first one give us 12x to the power 3 minus 12x squared minus 24x, right? Then the 5 will be 0. So this expression here is what you are going to simplify and equate it to 0. So 12x cubed minus 12x squared minus 24x should be equal to 0. This equation should give us our critical point, okay? And from the critical point, you know how to find the increasing and the decreasing portions of the function. So to simplify such an equation, you have to make your x the subject, and we're getting 12x squared minus 12x minus 24 is equal to 0. Is that not it? But even before, I can take away the 12, right? So that to make it simpler, x multiplying x squared minus x minus 2 equal to 0, like this, nicely. So once I have this, I will say that my very first value of x is equal to 0, right? That's one peak. X is 0. That is the outside one. Then the next part is x squared minus x minus 2 is also equal to 0. Then I have to just simplify this, right? I have to just simplify this. So how do we break this down? How do we break this down? So you can punch on the calculator so that you get the root of this equation as simple as possible, right? So let's see. So I have 1, I have negative 1, right? And I have negative 2. So meaning that you are going to have x plus 1 multiplying x minus 2, right? Is equal to 0. And that is what we give us. So meaning our function should be, our root to be s is equal to 0. Here will give me s is equal to negative 1. Then finally s is equal to 2. So these are the three critical points of our function. The three critical points. Okay. And as I told you, our function kept increasing until it reached this level, right? This level. That was a critical point. Okay. Then it came down until it reached another level, another critical point. So at every critical point, there is a change in direction. That is the idea. At every critical point, there is a change in direction. So we will let this critical point guide us in finding the intervals at which our function is increasing and is decreasing. Let's see. Okay. So let's see. I'll have my critical points on a number line. So I have 0, negative 1, 2. So 0 will be at the center, negative 1 will be here, then 2 will be here, right? Then I'll draw partition. I'll draw partition, right? So meaning I'll have how many intervals? I'll have 4 intervals. This one from this side to this side is 1. Between this and this is 2. Between this and this is 3. Then finally from this side to this side is 4, right? So what do we do? All that we are trying to do is we put our function, we put any value here to test our derivative to see if our derivative is what, increasing or decreasing. Is that not it? So what is our derivative? Our derivative was this, don't forget. So you have 12x cubed minus what, 12x squared minus 24x. When you have the left side of negative 1, I can put negative 2 inside this function. So when you put negative 2 inside this function, what do you get? So putting negative 2 inside this function, you simply have 12 multiplying negative 2 to the power of 3, right? Then minus 12. Just put this on your calculator, okay? Then minus 12. So I'm just substituting, I've chosen any random number here. So f prime of what? Negative 2. That's what I'm doing. Then minus 12 times, open brackets, negative 2 all squared, right? Then finally minus 24 multiplying what, x, which is negative what, 2. Is that not it? So 24 multiplying 2. So this is giving me and negative 96. I had negative 96. And what is telling me that this is a decreasing what part? Decreasing. Okay. So I simply write what? Decreasing. Decreasing. Okay. So meaning this is decreasing. Then I come to this side. This side, I can what value can I choose? Don't choose the critical point because they'll obviously give you zero. So any number within here. Then I can choose something like from 0 to negative 1. I can put something there, which is let's say f prime of negative 0.9, right? That will also be, let me make it negative 0.5. That will be, because from here I'll move to negative 0.5 before I what increase towards negative 1. Is that not it? So let's change the values we inputted first to negative 0.5, and that alone should be negative 0.5, right? And that is giving me positive 7.5. So f prime of negative 0.5 is giving me 7.5, meaning this is what? Increasing. Okay, this is increasing. Very important. The next one is f prime of, what do we choose here? In between 0 to 2, we can put f prime of 1. Just change the value here again to 1. Just put 1 there. Okay, simply put 1 here. And that is giving me negative 24. So once I have negative 24, meaning decreasing, I put decreasing, right? Then finally, f prime of 3 will be, because anything greater than 2, you can choose 3. You just have to make this substitution. You're having 3, 3, then 3. And that is giving me 144. 144. Okay, so meaning this is what's increasing. So I have this four regions: decreasing, increasing, decreasing, increasing. We have to simply write the interval. So this side, remember, it is what? From negative 1 to what? Negative infinity. So our interval is simply negative infinity, comma what? Negative 1. Like this. When I come here, it's from what? Negative 1 towards 0. Like this. When I come here, it's from what? 0 towards 2. And finally from what? 2 to what? Positive infinity. As simple as that. So the question was like, we should find the interval. So these are the intervals, the four intervals. That is all. That is all. Solve this problem. So now let's quickly move to the next part of our problem. Yes, there's a review tutorial. So we're going to solve different forms of problems so that you know how you can solve these tasks and you get a grip and you don't get lost. You don't get lost. All right. Okay, so our fourth question. Find the critical points, then endpoint of the domain of f. So we are looking out for critical points, then endpoint of the domain of f. The value of the function at each of these points, and identify the extreme values of this function and this function. Let's take the first one. F of x is equal to x square root of 4 minus s squared. Okay, we are looking out for the critical points, endpoints of the domain of f, then also the value of the function at critical point and also the endpoint. Okay. Then after we look out for the extreme values. So this is a combination. So we are looking out for the minimum and the maximum value. That's the application problem. Okay. Application problem. So see, the first one is critical point. To find a critical point, what do? We need to simply differentiate this function and equate it to 0. Okay. Differentiate it and equate to 0. So I have x square root of what? 4 minus s squared. And I want to differentiate this function. How do I do that? I have to transform this nicely to be x multiplying 4 minus s squared all to the power half, right? This should be equal to f of x. If I want to differentiate this, I think now this is going to be good. Okay, so this is going to be good. So at this point, We can use product rule for work to make things simpler. It's actually a composite function, but we can use product rule to also work. So using product rule, I'll take x alone and I'll take this alone. When I differentiate x, I get 1, right? So x differentiated as 1, multiplying 4 minus s squared all to the power half, plus maintaining x, right? Differentiating this expression. We want to differentiate this expression. This whole expression is a composite function. You first differentiate the entire function as what? 1 out of 2, 4 minus s squared to the power negative half. Then you multiply it by what? Differentiating what is inside. Now differentiate what is inside, I'm going to get negative 2x. And this will be equal to f of what? F prime of what? X. So at this point, I'll simply have 4 minus s squared to the power half plus here will give me, so let's see, this is negative 2x, right? I'll multiply that by this and I'll have negative 2x squared, that is this and this, okay? Then I'll handle what is inside, that is half, right? Half multiplying 4 minus s squared negative half by this equals f prime of x. So at this point, let's see, this half can take this 2 away nicely. Then let's see something here. Here is the same as square root of what? 4 minus s squared, so that becomes simpler, plus negative s squared mod over, this is simply square root of what? 4 minus what? S squared, as simple as that. 4 minus s squared is equal to f prime of x. So at this point, I can say that my critical point is 0. Then I'll equate this to 0. 4 minus s squared plus negative s squared over 4 minus s squared under the square root sign is equal to 0. So what do? I'll multiply through by what? My denominator. Then I'll be getting what? When I multiply this and this, I'll get 4 minus s squared because the square root will cancel, plus negative s squared multiplying 1, right? Because this will cancel, so I get negative s squared multiplying 1 is equal to 0, right? So at this point, you are almost at the point. So this gives me 4 minus s squared minus s squared is equal to 0, which is the same as 4 minus 2s squared is equal to 0, right? So at this point, what do? This is quadratic, is that not it? I can factorize my 2 out, and I'm going to get 2 open brackets, 2 minus what? S squared is equal to 0. I'll cancel out and I'll still have 2 minus s squared. These two go because when I divide. So 2 minus s squared is equal to 0. And I'll get s to be equal to plus or minus what? 2. As simple as that. So my critical point is s is equal to minus 2, comma what? Positive 2. Those are the critical points, right? So the question was asking us to find the critical point. Then we find the corresponding values of the critical point here. Remember, since the x here is squared, we can easily predict the value. So what are the functional values? So I'll find f of negative 2 to be equal to, I'll simply put negative 2 inside what I have here. I'll have negative 2 multiplying the square root of 4 minus negative 2 squared will be 4, obviously, right? Minus 4, and that is 0. So f of negative 2 is 0. Then f of positive 2 obviously will also be what? 0. And why do I even find it? Because it's already the critical point, so it will usually give me 0. Yes. So that is what we have found. That is what we have found. That's all we have found. Now the next thing is we should find the endpoint of the domain of f. What's the domain of f? Domain of f. Remember that for f to be defined, we are going to have what's inside the square root, which is 4 minus. We are simply going to have in this down. We are simply going to have 4 minus s squared to be greater than or equal to what? 0, right? So this is the same as what I can, this difference of 2 squared, is that not it? Yes. So I'm going to have 2 minus x. I'm going to have 2 minus x multiplying 2 plus x, right? Is greater than or equal to what? 0. Okay. So to find the endpoint of my function here using the domain, right? Using the domain of this function, then I'm going to have two parties. I'm going to have two parties. Okay. So I'll have the root of this equation actually will give us what? 2 and negative 2. Is that not it? 2 and negative 2. And since you are using greater than or equal to, I'm going to have x to be less than negative 2, less than or equal to negative 2. Then x should be greater than or equal to what? Positive 2. Positive 2. Like that. So these are the two endpoints. So actually, our endpoint, and it says that we should find the value of the function at each of these points, and after we identify the extreme values. Extreme values. So then, using the domain, you realize that our endpoint is obviously the same as what? Our critical point. Obviously. So let's see if we can picture this function somewhere. Picture this function somewhere. So this function can pictorially, let's see something here. So pictorially, we can say that our function, once you have this, we have negative 2 and 2 as the endpoint. So I have negative 2 here, then I have 2 here, and I'm saying that the function is defined over this portion and over this portion. So the values of x that will make this defined. So now let's see something here. But x is squared, right? X is squared. So that is one thing we should take note of. If x is squared, sometimes you have to use logical reasoning to find your endpoint. So let's apply logical reasoning and see if it will be the same. Once you have a function f of x to be equal to this, you are looking out for the endpoint of this function. You know that when s is negative 2, s is negative 2, yes, obviously you are going to have, and once s is squared here, whether it's negative or positive, we only, our interest is in the magnitude. Okay, our interest is in the magnitude. Take note. Because of that, if you get negative 4, negative 5, this function will not be defined. Take note. Anything less than negative 2 will not be defined. Anything here, our function will not be defined. Then anything greater than negative 2, or anything greater than 2, which is what? 4, 5, 6, that will also give us a negative value. So this one to another part, okay? This one to another part. Meaning that this here is giving us the elimination of what? Our undefined inputs. For that reason, our interval will be from here to here. That is from negative 2 less than or equal to x less than or equal to 2. That will be the only endpoint of our function. Okay, so our function is having the peaks at negative 2 and 2, right? And they were all giving 0. So it will start from here, then it moves towards 2. That's all. It's peaking at negative 2 and 2 because it is not valid at anything less than negative 2, anything more than 2. Okay. So when you take the output of this, you realize that you are still be getting what? Zeros, zeros, zeros. So obviously extreme values are the same thing. Our extreme values are what? Negative 2 and what? 2. Is that not it? As simple as that. Negative 2 and 2. Our extreme value should be negative 2 and 2. Okay. Then we're looking out for the extremes, is that not it? And you know extreme, you have minimum and what? Maximum. So obviously our minimum value will be what? Our minimum and our maximum value are simply what? The negative 2 and the 2, right? So sorry, the minimum extreme values will be the value after. So that will be zero. That will be zero. These are just the critical points and the end points. Okay. So when you put this into the function, it gives you the what minimum and the maximum value. So it will be zeros, and that is for the first function. Now we have another function x squared square root of 3 minus x within. So we can tackle that one as well. We can tackle that one as well. Right. So let's see how we do that as well. Simply get. So the next function f of x equal to x squared square root of 3 minus x. Okay, square root of 3 minus x. So we realize that for this function, what you're going to do is, for this function, what we are going to do is, the first is critical point. So f prime of x, what would that be? I'll first take x squared and differentiate. I'll get 2x multiplying by root of 3 minus x plus, I will maintain my x squared, then I'll differentiate here. When I differentiate here, remember this is what? To the power half, okay, as we did before. You get half 3 minus x all to the power negative half. Is that not it? Right? Multiplying what? When we differentiate what is inside, and that will give us negative 1. Simple as that. So I'll keep on, I'll get 2x multiplying square root of 3 minus x plus, here is x squared, then this is negative 1, okay? So negative x squared here, let me make it that way. So negative x squared over 2 multiplying what 1 over the square root of what 3 minus what x, and everything here should be 0. So 2x root of 3 minus x squared over 2. So let me make it x squared over 2 root of 3 minus x should be 0. At this point, what do? I multiply through by the expression 2 multiplying root of 3 minus x, and that'll give me, yes, 2, right? Yes, this place is 2. So this will give me 4, sorry, 4x, right? Then the inner function will cancel, the root will cancel 3 minus x, okay? Minus this one 2 will cancel, x squared equal to 0. So we expand 12x minus 4x squared minus x squared is equal to 0. And this is going to give me 12x squared minus 5x squared is equal to 0. 12x, sorry, 12x. There's no squared here. 12x. Okay, so 12x minus 5x squared is equal to 0. At this point, I factorize x out. I get 12 minus 5x is equal to 0. X will be equal to 0. And I'm going to have x to be equal to 12 over 5. Okay, so these are my critical points. My critical points, x equals 0. Then x is equal to 12 on 5. Then I find the functional value of this. Okay, I find the functional values of this. And, I'm going to have, once x is 0, obviously our function will be 0, okay? So f of 0 will be equal to what? 0. Is that not it? Then our f of 12 on 5 will be equal to, we put 12 on 5 here. What are you getting? So 12 on 5 squared, 12 on 5 squared, right? Times the square root of 3 minus 12 on 5. And that is giving me 4.46, right? 4.46. 4.46. So we are having 0, then 4.46. We put them down. Then now let's see the extreme values. What should be the extreme values of this? So coming back to our domain, let's apply what we did here. So coming back to the domain, you realize that you are going to get x squared square root of 3 minus x. Once you have this expression here, if you want to find the domain, our interest should be there, 3 minus x, okay? So what are the values that will make 3 minus x undefined? Or what will make it defined? Or what is the range of value 3 minus x will be defined? That will be our domain. So 3 minus x should be greater than or equal to what? 0. Is that not it? Therefore, obviously, x should be less than or equal to what? 3. Is that true? When I put any number, if I put 3 instead of I get 0, any number less than 3 will give me what? Yes, positive number. That is true. So meaning that our extremes will be what? S is less than. So from negative infinity, comma what? Sorry. Negative infinity, comma what? 3. Is that not? These are our extremes. So we should only find 3 because negative infinity is not of interest. So now let's find f of 3. F of 3 will be what? 3 squared multiplying what? 3 minus what? 3. Is that not it? And this will be what? 0. 0. Okay, 0. So meaning our extremities, we are having the we are having 12.5, which is our critical point here, to give us our maximum. Okay, this is giving us 0, this is giving us what? 0. So this is obviously the big one. But actually we're supposed to use the second derivative test to know the minimum one among this, the minimum and the what? Maximum. Okay, so using the second derivative test, after our first derivative, we have this expression. But going again to simplify this for second derivative, it's going to be a tedious one, okay? So we can just use our values here to test. Okay, values here to test, because if this is giving you positive number, obviously that number will be what? Up. And then it's going to give us what? A peak which is higher. This is giving us 0, obviously, to lie down. So this will be our maximum. And this is a point of what? Inflection, okay? Or point of inflection. It's 0. 0, the point of inflection. So x is less than negative 3 is also giving us 0. That one was just an endpoint. Okay, was just an endpoint. And that is how we solve the fourth question. Okay. Then the final question on our list, we say that we should optimize the height, something. So let's get straight to that too. So we are having the height of a moving body. Yes, the height of a body moving vertically, right? Is giving us h of t is equal to half gt plus v naught t plus h naught, where g is greater than 0. Find the body's maximum height in terms of what? H naught, in terms of v naught and g. Maximum height. How do we do this? This optimization. We want the maximum height. Maximum height. Okay. So at the maximum height, what do? You realize that you have h prime of t. You first find the derivative, how h is changing with respect to t, to be equal to, here I'll get what? Half g, right? Plus v naught. My h naught is obviously 0. Okay, obviously 0 because there is no t. Now, once I have this, the next thing is we have to find the critical point. Okay, we have to find a critical point. So what are we actually finding? So let's see something. Once you have found our derivative here,